Okay, so another fairly short section here. We're going to talk about Rolle's theorem and the mean value theorem. There are a lot of results that we've been using that we haven't really proven because their proofs rely on the mean value theorem. Okay, so you can go back and look at some of the stuff that we did, especially like 4.1, 4.2, 4.3 stuff, and probably understand a little bit better where the theorems are coming from now that you're going to take a look at the mean value theorem. Mean value theorem can be proven pretty easily once we have Rolle's theorem. And Rolle's theorem I'm actually not going to prove too because it's a pretty obvious fact that is kind of a consequence of some things that we've talked about already. But anyway, here's Rolle's theorem. So it says, let f be continuous on the closed interval ab and differentiable on the open interval ab. If f of a equals 0 and f of b equals 0, then there exists a point c in the interval from a to b such that f prime of c equals 0. Okay? And here's a picture of what we're talking about. So if you have this function and it's continuous and differentiable, then and if the function is 0 at the two endpoints of the interval, then somewhere within the interval there has to be a place where the derivative is 0. In other words, there has to be a place where you have a horizontal tangent line. That has to be the case because the function has to turn around somehow. And if it's differentiable, then it doesn't have any sharp points, right? So differentiability is really key, right? This function here is not differentiable at 0, and that happens to be where the function turns around. And so it would not be the case for this particular function that just because f of -1 is 0 and f of +1 is 0, but there's no place in between where the derivative is equal to 0, because the one kind of candidate for that is the function is not even differentiable there. Okay, so the differentiability requirement is key, right? The function has to be differentiable on AB, and if it is, then that means it's got just these smooth curves, which means you've got to have a horizontal tangent line somewhere. The other thing that I'll point out about this theorem is that the theorem says that there exists a point. What that means is that there exists at least one, right? There's at least one point C where this could happen. So like here's a picture where you actually have two places where you have horizontal tangent lines in between the two endpoints, right? And you could have, infinitely many, in fact. So anyway, that's that. The proof of this theorem is basically a consequence of the extreme value theorem. Remember, the extreme value theorem says that if you've got a continuous function on a closed interval, then it's going to have a maximum and a minimum on that closed interval. So we're continuous on a closed interval, and we're differentiable on an open interval. The two endpoints are 0, so you know that unless the function is a constant function, which, by the way, if the function is a constant function, then it is trivially true that the derivative is going to be 0 at every point in between the endpoints. But if it's not a constant function, then it's got to either rise above or kind of fall below the x-axis. In which case, you're either going to have a maximum or a minimum somewhere in between, right? So it's basically a consequence of the extreme value theorem. Okay. So let me give you an example of Rolle's theorem in action. So that I don't have to write this out again. You can kind of pause the video and write this out. But anyway, let's do this example here. Let's find the two intercepts of f of x equals x squared minus 5x plus 4. So it has two x-intercepts. Let's find them, and then let's confirm that since we're crossing the x-axis in those two places, there must be a place in the middle somewhere, such that the derivative is 0. So let's confirm that that's true. So here we go. So our first task is to find the x-intercepts of this function. If we can factor it, then that's going to be pretty easy. And I think we can. This one goes to x minus 4 x minus 1, right? So the x-intercepts are 4 and 1. Okay. So now we found the x-intercepts. Now we want to confirm that there is a c somewhere between 1 and 4, such that f prime of c is equal to 0. So we want c somewhere in the interval from 1 to 4. I don't know if I've used those symbols with you before, but this just means that c is in the interval from 1 to 4. So we want to see somewhere in this interval from 1 to 4, such that f prime of c equals 0. Well, let's find the derivative of f, right? F prime of x is 2x minus 5, and we want to set that equal to 0, and then solve for x. So we would add 5, divide by 2, we'd get x equals 5 halves. Notice that 5 halves, 2 goes into 5 twice with 1 left over. This is just 2.5, right? It's 2.5. And sure enough, 2.5 is in this interval. So I suppose, to make it more clear, we could say c equals 2.5. Okay. So yeah. In fact, knowing what you know about parabolas, you probably realize that this is the vertex, right? It's got to be the x-coordinate of the vertex. So you could kind of draw a picture of this scenario now. You know that you've got 1, 2, 3, 4 x-intercepts here and here, and then you've got a vertex in between. This parabola opens up, so it must be a minimum, right? So 1, 2.5, so there it is, and it's gonna look something like this, but whoops. But clearly you've got this horizontal asymptote right there at the vertex. Okay, so that's that one. That's Rolle's theorem. Okay, so Rolle's theorem. Now we're going to use Rolle's theorem to prove the mean value theorem. And here's what the mean value theorem says. So mean value theorem says that it says let f be a continuous function on the closed interval from a to b, and let it be differentiable on the open interval from a to b. So same conditions as Rolle's theorem so far. But this time we're going to say if those conditions hold, then there's a point c in the interval from a to b such that f prime of c equals f of b minus f of a over b minus a. In other words, there must be a point where the tangent line, f prime of c, is parallel, well, the slope of the tangent line, right, is parallel to the secant line, f of b minus f of a over b minus a, right, the secant line connecting points a and b. Right? So pictorially it would look like this, right? So you've got your secant line between a and b. The slope of this secant line is f of b minus f of a over b minus a. And what the mean value theorem tells us is that there must be a point c somewhere in between a and b such that f prime of c, so the slope of the tangent line, is parallel or is equal to the slope of the secant line, right? So the tangent line and the secant line are parallel. Another way to say the same thing is that there must be a point somewhere between a and b where the instantaneous rate of change is equal to the average rate of change. Okay, so f of b minus f of a over b minus a, that's the average rate of change. F prime of c is an instantaneous rate of change, and we're saying that there must be a point c between a and b where that instantaneous rate of change is equal to the average rate of change. Okay, so this is what mean value theorem says. And it's pretty straightforward as well, I think. But let's prove it. It's kind of a fun one to prove. So, proof of the mean value theorem. So first of all, note that the secant line joining a to b is given by this formula. Right? We can call it y minus f of a equals the slope of the secant line times x minus a. So it's y minus y1 equals m times x minus x1, right? Only instead of y1 we're calling it f of a, instead of x1 we're calling it a. And this is just the formula for the slope. Okay, we can solve that for y, right? Move the f of a over. We get this. So we'll keep that in the back of our minds. Now, let v of x be the distance between f of x and the secant line. Okay, then v of x is f of x minus the secant line, okay, that we just came up with up here. Now, what can we say about v of x? Well, we know that f is continuous. So f is continuous, and therefore v must also be continuous, because v is just the difference of a continuous function and a bunch of other continuous stuff, right? Like these are all just numbers. So this is just a linear function, and linear functions are continuous. So you have a continuous function minus a continuous function, that's going to be continuous, right? So since f is continuous on AB, v of x is continuous on AB. We also know that f is differentiable on the open interval AB, and that means v of x is also differentiable, again, because f is differentiable, linear functions are differentiable, the difference of two differentiable functions is differentiable, okay? So since f is differentiable on AB, so is v, okay? Alright, so that's interesting, right? Because that means that v of x satisfies the conditions, the first two conditions of Rolle's theorem, right? That it has to be continuous on the closed interval and differentiable on the open interval. It also satisfies the next condition of Rolle's theorem, right? Because v of a equals 0 and v of b also equals 0. Now you can verify that. If you plug in a, v of a would be f of a minus, all this stuff, times a minus a. So that's all just going to be 0 plus, f of a. So it's just going to be f of a minus f of a. Well, that's 0, right? So v of a is 0. V of b is going to be f of b minus, all this stuff times x times b minus a plus f of a. Well, the b minus a's will cancel, and then the f of a's will cancel, and then the f of b's will cancel, and again you'll get 0, right? Okay, so Rolle's theorem applies here. By Rolle's theorem, there must be a c in the open interval AB such that f prime of c is equal to 0. Now, on the other hand, we could take this function and differentiate, right? F prime of x would be f prime of c minus, well, if you were to distribute this slope, then you'd get something times x minus something plus something else. But those are just constants. They're going to disappear when you take the derivative. And as for the slope times x, well, when you take the derivative, it's just going to be the slope, right? So f prime of c equals f prime of x minus the slope, right? That means f prime of c is f prime of c minus the slope. But v prime of c is 0, right? Okay. Well, so then you can add this over to the other side, and you get f prime of c equals f of b minus f of a over b minus a. Sure enough, right? We've found a c such that the instantaneous rate of change is equal to the average rate of change, right? Which is the statement of the mean value theorem. So there's the proof, right? It's a nice one. I like it. So one more example, and then that'll be it for this section. Like I said, a really short section, which is good because you have a test coming up, and so I don't want to overload you with a bunch of new material right before your test. But anyway, so number 2 here says verify that the hypotheses of the mean value theorem are satisfied for this function f of x equals x minus 1 over x on the interval from 3 to 4. And then find all c in the interval from 3 to 4 that satisfy the conclusion of the theorem. Okay, let's do it. So the hypotheses of the mean value theorem are, number 1, that f of x is continuous on the closed interval 3, 4, and then number 2, that f is differentiable on the open interval from 3 to 4. Okay. Neither of those conditions is there's not a lot to show in terms of proving that, I guess. As far as the continuity is concerned, the only place where this function ceases to be continuous is at x equals 0, because you get a 0 in the denominator there. Everywhere else, this function is continuous. But see, 0 is not in this interval. So maybe we could say something like that. We could say, okay, so this was example 1 up here. Example 2, we could say, alright, so f of x equals x minus 1 over x. So we could say something like this. Note, f is continuous on all real numbers except 0. But since 0 is not in the interval from 3 to 4, f is continuous on 3, 4. Okay, so that's the first condition. The second condition that we have to check is that f has to be differentiable on the open interval 3, 4. Now to check that, we should probably take the derivative and figure out where the derivative exists, I guess. So f prime of x would be 1. If I think of this as I'm thinking of this as x minus x to the negative 1. So that's going to be a plus x to the negative 2. So plus 1 over x squared. Okay, so this was, by the way, for the first condition. For the second condition now, we can say this. So f prime of x is continuous. Or sorry, f prime of x, we'll just say is defined for, or we'll say on R, except, once again, at 0, right? But again, 0 is not in the open interval 3, 4, so we can say since 0 is not in the open interval, we'll say f is differentiable on 3, 4, right? So the derivative exists everywhere except at 0. So in particular, the derivative exists on the open interval from 3, 4, and therefore the original parent function is differentiable on 3, 4. Okay, so the conditions are satisfied, right? So those two conditions, check and check. The hypotheses are satisfied. Now we're supposed to find all C in this open interval that satisfy the conclusion of the theorem. Well, what's the conclusion of the theorem? The conclusion of the theorem is that there is a point C in the interval such that f prime of C equals the average rate of change. So it might be good to figure out what the average rate of change is. Okay, so the average rate of change on the interval from 3 to 4 is going to be, maybe I'll call it m average, right? So it's going to be f of 4 minus f of 3 over 4 minus 3. F of 4 is 4 minus a fourth. F of 3 is going to be 3 minus a third. And 4 minus 3 is just 1. Anyway, you could plug this into your calculator now. Or if you want to do it by hand, I guess you can. I don't feel like getting common denominators right now, so I'm going to do it in my calculator. 4 minus 1/4 minus 3 minus 1/3 is 13/12. Okay. So, what the mean value theorem says is that there is a place where the derivative is equal to 13/12. So let's see if we can find it. So let's take f prime of x, which we've already done. It's 1 plus 1 over x squared. And we want to set that equal to 13/12 and solve. Okay. So if I subtract 1, 1 is 12/12, right? So I would get 1 over x squared equals 1 over 12, which means that x squared equals 12, right? Which means that x is plus or minus square root of 12. That would be 2 root 3. 2 times the square root of 3. Now obviously negative 2 root 3 is not in the interval, okay? We're looking for a number between 3 and 4. So negative 2 root 3 is out. What about positive 2 root 3? About how much is that? 2 times square root of 3 is 3.4641 approximately. Okay, So so that does the trick, right? So we would say, okay, so C is 2 root 3, approximately 3.46. All right, and that's that. So that's all I have for this particular section. We'll see you in the next one.